we'll start in 2 to 3 minutes, waiting for others to join, and then we can start. Okay, it's already 3:05. Let's start. So let me just share my screen first. Yeah, just a second. Just give me a second. Yeah, it's fine. So good afternoon, everyone. My name is Musa Rafiq. I'm a PhD student in the Department of Electrical Engineering at IIT Kanpur. I'm the course chair for the course CMOS Digital VLSI Design. The course is taught by Professor Sudev Dasgupta from IIT Roorkee. This is live session 6. Basically, what we do in live sessions, we solve problems pertaining to that week's content. And this is a 8 week long course, as you might be knowing by now. And after this, only 2 more sessions will be remaining. So this is the course layout. You guys are familiar with this course layout. And what we are doing here in week 6 will be discussing questions related to sequential logic design. So I was looking at the assignments and the contents that you have so far studied. So in the sequential design, so only some basic questions were discussed in the assignment, and so I'm able to only create problems pertaining to that. And today's lecture will be related to basics of sequential logic design, and next week will be much more comprehensive. And I wanted to give one more information. What typically used to happen is we used to have one more extra session at the end of the course for revision class, but due to some actually, I'm running on a very tight schedule. I won't be able to take an extra class, extra session after the 8th session. So what I'm planning to do is in the week 8, that is just a second, I'll admit a person. Yeah. So what I'm planning to do is on the live session number 8, that is the last live session of the course. I'll dedicate half of the time for that week's content, and half of the time I'll pick some problems. I'll cherry pick some problems from the previous week's content, and we'll just have a brief revision. So typically, we used to have an extra section that was completely voluntary. NPTEL guys used to share information about that, but this time I'm running on a very tight schedule. I won't be able to have an extra session, but I'm planning to give a revision of some of the questions in week 8. I hope that's clear with everyone. And today, mostly what I found in the assignment of week 6 and also the content, questions were pretty basic. So some of the questions may appear basic, but it's what it is. I can't really help with that. But next week, we'll dive deeper into sequential design. And also, I have put some questions that are from basic digital circuits course. Maybe some BTech students are here, they will find it important from the gate point of view. That's why I put them here, couple of questions. And at the start of the lecture, I also have an introduction of sequential circuits, some basic timing definitions, and what are the sequential circuits. We'll just cover that part. Regarding the guidelines, actually, I'm bound to use these guidelines every. Can you please confirm? Are you able to see the slideshow? Can anyone confirm? I don't think so. Just give me a second. Just give me a second. I'll just share the whole. Okay. Okay. There was some lag. Okay. On my tablet, I am not able. Okay, anyways, so if any point of the time you are not able to see the screen, please prompt me. Right now, I'm in a slideshow mode. Can anyone please confirm? Are you able to see this pointer? Can anyone please confirm? Okay, this pointer I'm seeing. This. Okay, do tell me if you don't see that. Yeah. So I'm bound to repeat these guidelines every week. So first of all, you should join with your authentic usernames. No fictitious or inappropriate usernames will be added to the session. Then camera and microphone etiquette. So all participants must keep their cameras turned off and microphones muted during the session unless explicitly asked to unmute. Sorry. So now the roll is pretty low. So you can always unmute yourself after the question is solved and asking your doubt. So I don't think that will be a problem now. It is basically for when the class roll is very high, that time sufficiently large, so that time it creates a problem. And regarding questions and doubts, sufficient time will be given after every problem for asking your doubts. And as you already know, session is being recorded and it will be uploaded to YouTube, and that YouTube video link will be shared on the Google Sheet as already shared by the NPTEL team. And today's lecture, I feel like will not be that long, so it may be last hardly for 1 hour or 1 hour 10 minutes because I couldn't find much. I couldn't create sufficient problems out of what you have studied in this week, and also the I have to align myself. And what I have to do is I have to align myself with the contents in the assignment. So in that regard, I was not able to create some comprehensive problems as well. So it was a limitation, at least not from my end. But anyways, I have put some basic problems as well, and I'll also give an overview of the sequential circuits, just a brief overview, hardly for 5 to 10 minutes, and then we can start with the problem. Now, if you have some follow-up questions pertaining to this week or previous week's problem-solving session, you are always welcome to reach out via email. I'll be more than happy to answer your queries. So, are you able to see this slide, sequential circuit slide? This the title with sequential circuits. Anyone please confirm in the chat box, or are you able to see this sequential circuit slide? Anyone? Actually, on my tablet, I'm not able to see it. That's why I'm asking for your confirmation. Yeah, that was the case. Yeah. So let me just share it again. Some kind of a. Now, are you able to see this? Not only the screen, can you confirm whether you are able to see this pointer? No, you won't be able to see it. I have to share the entire screen. So just give me a second. Yeah, this is an issue with Google Meet. It happens frequently. So I'll just share an entire screen. Yeah, that's that's what I wanted. Yeah. So yeah, so let's just give the brief overview of sequential circuits. I think by now you all must be familiar with this. In your lecture notes, you might have got the idea. So far up to this point, we have studied the combinational circuits, right? Now we are coming to the sequential circuit parts, which are more prevalent in the real world. So real world ICs and real life circuits are made up of these sequential circuits. So what is a sequential circuit? Before we going to sequential circuit, the combinational circuit, what it is basically a function of only current inputs. But what is there in sequential circuit? Output is a function of current as well as preceding inputs. That means it needs some kind of a state to store the previous output or previous state. So that means it must be having some kind of a memory element, right? So most circuits that you see in your real life are FSM. What is this FSM? These are finite state machines. Simply a combinational block plus the registers that holds the system state. So here I have one example of this finite state machine. So here I have a combinational logic, as you can see here. Here I have an M input logic input that goes to this combinational logic, and it provides a logic output N, and also provides a next state of N Boolean inputs. So this is the next state of N Boolean inputs and Boolean variables that goes to the memory part, and that is driven by this clock. So can either be an edge level it can either be a level edge, or so what should I say? It can either be an edge or a level triggered flip flop, and this gives me an output which is the current state, which is also of n boolean variables. So based on this logic input and current state, my output is defined. So I can say that the sequential state output is function of input, present input and preceding inputs, so which define the state of the system. And as I already told you, most circuits are finite state machines, that combination of combinational circuit plus the registers. And and also this part here, this data is being sampled only at the positive or negative edge triggered or negative edge of the clock. So basically what happens is, most of this flip-flop or register, they are edge triggered, means when the clock makes 0 to 1 transistor or 1 to 0 transistor, only then this data can be sampled here. So when it is triggered, like when 0 to 1 transition triggers it, it's called positive edge triggered, or when 1 to 0 transition triggers it, it's called negative edge trigger. So basically a clock transition, at a clock transition, data is sampled. So output, as I already said, will be function of current inputs as well as function of current state here, current inputs and current state. In the next state, okay, so we have already discussed that output is a function of current state, which is defined by past inputs right here and current inputs. So next state is obtained as the output of a register when fed with n bit inputs. So we have already said that. And edge triggered. So next state bits, this here, next state bits are sampled and fed to combinational block only at a particular time interval. So mostly we are talking about edge triggering. So only when the clock edge triggers, it is being sampled. So what happens? Register ignores all other changes until the next edge. So whatever happens till then, this block, this memory register block, will ignore those changes and it only sample until the next edge. So we have these synchronous circuits. What are these synchronous circuits? So synchronous circuits are circuits in which all the registers are fed by the same global clock. So everything is being maintained by the one clock, which triggers switching events. And one thing about this is that next cycle can't begin unless all computations have been performed. So that means the time period should be such that all computations should be performed in a sequential circuit. Unless those are not complete, we can't begin with the next clock. One thing I want to ask in here, you can use chat box to answer your question. So how is clock being generated in the circuits? Do you know how clock is being generated? Clock pulses. What is the mechanism of generating clock pulses? Anyone? 555 timer. But what's the heart of it? Can you please elaborate on that part? Even inverter needs an input, right? Yes, quartz crystal. Yeah, that's what I was looking for. It's basically quartz crystal. Exactly. So what you can do is you guys can look up for this and see how a clock is generated in a IC. It's kind of a fun assignment for you guys, and maybe uh, next time we can discuss. So some text three. Okay. Now I have another slide which talks about timing definitions in a sequential circuit. So before we start, here I have an example of a sequential circuit which has a combinational block logic shown by this box, and underneath is the sequential this memory element, a simple D flip-flop. Which is what D flip-flop does. It output Q gets sampled by D gets sampled at Q node only at the triggering only at when the clock triggers. And from the figure, we can see it is a positive edge triggered flip flop. So here, if there was a bubble, it would have been a negative edge triggered flip flop. So input M, I have my output N, and the next state having N Boolean variables, and then it goes is being sampled only at positive edge triggering. So now talk about some waveforms here. So what we have here is we have a clock, and this is your 1 to 0 transition. So here nothing will happen, and this is your 0 to 1 transition, or this is of interest for us. So there are some timing definitions which I would like to discuss first. So when we have this 0 to 1 transition, at this transition only my data is being sampled, but there is some time before this transition before which my data needs to be stable. So that time is defined as setup time. So setup time is defined as a time before which data needs to be before the occurring of clock edge, for which data needs to be stable. So you can say from this point to this point, and before that data can vary. I don't care about that, but in this setup time my data can't vary. And there is also one more time which is called as hold time, which is the time duration for which my input should be stable after a clock edge. So you can say from this point to this point, and this is known as hold time. Basically, the time after which data needs to be stable is known as hold time. And after that, my data can vary. I also need not to care about that. And then there is also a time which is basically from the triggering of clock edge to the point where my state changes. So that is basically clock to Q delay. So basically, once the triggering happens and then my D gets sampled to Q, how much time it will take? Why it takes time? So because these flip-flops, these sequential circuits are also made up of some combinational circuit block, right? So these combinational circuit block will have some delays and which give rise to this clock to Q delay. So what we have here is we have a setup time, time before the clock is during which data input must be valid. I won't go into the physics of it, why we need setup time and hold time. You can refer to our lecture notes or some reference materials, because this is a problem solving session. I have just left that part. And then the whole time after which the clock edge for which data input must remain valid. And there is also this propagation delay which gives rise to clock to Q time. Basically, worst case propagation delay with reference, because everything in sequential circuit is driven by clock. So everything will be talked in terms of clock edges. So clock to Q time, worst case propagation delay with reference to clock edge after which data is copied to Q input. Basically, from this point until I see a data being sampled. So now there must be constraints. So we have already said that, and also there is one more delay which is called contamination delay. So in combinational circuits, you have come across this term contamination delay. Basically, you might be knowing that output this delay of a combinational circuit is also dependent upon the input patterns, and so because of the some input pattern, sometimes I will encounter less delay and sometimes I will encounter more delay, and as a result there will exist some path on which there will be minimum delay, that is called as contamination delay. In the previous slide we told that all the computation should occur in one clock cycle. So there, because of that, there must be some constraints on the timing definitions. So there are three constraints that need to be fulfilled for one clock period. Firstly, When we have this one clock period, what should happen here is input to Q. Basically, the time taken from clock to Q needs to be covered in that input period, right? And then what we have here is we have combinational block uh, output should be present, and that combinational block output means it will take some propagation delay. So first I have told about this clock to Q delay that needs to be covered in this time period, and then also combinational block should also provide its output, right? So that is propagation delay of the combination logic. And also the third part is that output needs to be stable till the next clock edge, right? So next state means next state should be stable for next cycle, right? So that means setup time. So what it gives is it gives my t time period should be greater or equal to my setup time plus my propagation delay of the logic block plus the clock to Q delay of the flip-flop. So that puts a constraint on the time period. And also there is a constraint on the contamination delays. So what I have here is I have a contamination delay on some combination of inputs. I lead to a contamination delay. I have this input, which also leads to this contamination delay of the logic block, and I have this contamination delay of logic plus contamination delay of what should I say flip-flop. Now what happens here is that D that can vary this next state, but this next state should not be varied and before the hold time. So basically, in short, what I mean to say, minimum delay should be greater than the hold time. If I have to put in words, so minimal delay of a register is TCD register, and minimum delay of combination block is TCD logical block. So I mean to say that TCD of register plus TCD of logic should be greater than hold time. What I mean to say is this in his next state input should not change after this transition. So that means to say the contamination delay of this block plus this block should be greater than the hold time. So these are the two constraints that I have here. So time period should be greater than clock to Q delay plus TP logic plus TP setup time, and TCD register of this plus TCD logic should be greater or equal to hold. If it's not greater or equal to hold, it means that before the hold time my next state is getting changed. That means it's not being stable for this second. So I need it to be stable. So I need at least my contamination delays of this and this to be greater than the hold time. So these are some of the points I wanted to highlight in this lecture. I think now we can begin with the problem solving session. And at the start of the lecture, I think some of you were not there. What I told was that, let me go back to that point. So here we are discussing week 6 sequential logic design. So what I found in your lecture notes and in the assignments, I was not able to construct very comprehensive questions. So what I have done here is I have picked some basic questions from digital circuit course, that is the UG course, that will may help some people within their GATE exam. Some basic questions 2 3. And apart from that, I have also taken up questions that are aligned with your assignment problems, because if you have seen your assignment problems of week 6, they are pretty straightforward, mostly conceptual one-liners. And also one announcement I had made, that usually we used to have one extra session after the end of the course, that is after week 8's problem solving session. We used to take up one extra session and we used to discuss basically there was a revision class extra session where we used to discuss previous week's content, but I am having a busy schedule and I will not be able to take that. So what I'm planning to do is in week 8's live session I will devote my half of the time for week 8 content, and half of the time I'll be discussing uh, I picked cherry pick some problems of the previous problem solving session, and we will discuss those. If you have some problems, if you that you want me to repeat, or you have some doubt, you can always write an email, and then I think we can pick those problems. Otherwise I'll just hand pick some problems. So we can start with the first problem of today's live session. So I think you should be knowing the answer to this. So let me just share my screen on just give me a second. So I have the first question of today's live session. So any, yeah, I think people have already started giving answers. It's nice. So hold time in digital circuits is, I think we already discussed that. The time required for a signal to become stable after the clock edge. So basically this time. There is some physical reasoning behind it. So I have not discussed it. You can always refer to your books and lecture notes to get why this hold time and setup time exist. So correct option is option A. Now question 2. What is the setup time in digital circuit? The time required for a signal to become stable after the clock edge, the time interval when data must be stable before the clock edge. Option C, time change after clock edge, or option D, the time interval during which input data must be stable. Yes, exactly. Option B. This is your before clock edge, my data should be stable. Now, question third. Which of the following is not a sequential circuit? Anyone? Yes, D. Why? Any reason why? There must be a reason you have picked it. It's a combinational circuit, right? If it's not sequential, it's combinational. But what makes it combinational? Exactly. No memory state. Output depends on your current output, right? So you have this, let's say 4 is to 1 mux I1 A B C D, and you have this select lines S0 S1. Your output is only function of the select lines and the input. So it is basically I is equal to S0 S1 bar A plus S0 S1B plus S0 S1 C plus S0 S1D, right? So only function of present inputs, no memory involved. Now I have a question for you guys. So you guys solve it, then I'll show the solution. It should not take more than 2 minutes. So that's what I said. These week's questions are pretty straightforward. So for a positive edge triggered sequential circuit, the setup time and logic propagation time given are 3 nanoseconds and 2 nanoseconds. If the clock period is 10 nanoseconds, what is the maximum allowable clock to Q delay for correct operation? So what is the maximum allowable limit? You need to find what is the maximum allowable limit for clock to Q operation. Correct operation, maximum allowable CTQ delay. Some of you have done it, pretty simple. Just waiting for others to also do it. Yeah. So what we have here is we have a T setup of 3 nanoseconds, T propagation delay of 2 nanoseconds, and clock period of 10 nanoseconds. So for a correct operation, the condition we have is T clock should be greater or equal to T setup plus T PD plus T clock to Q. T clock is 10, 10 should be greater or equal to T setup is 3 plus T PD is 2, plus T C2Q. We need to find that implies T C2Q should be less or equal to 5. So the upper limit of T C2Q is 5 nanoseconds. Now question 5, it asks us a master slave JK flip-flop has a propagation delay of 6 nanoseconds for the master stage and the 4 nanoseconds for the slave stage. What is the total propagation delay from clock edge to output? So we need to find the total propagation delay from clock edge to output. So basically in a master slave what we have here is I'll write in a master slave. And by the way, if I think a couple of years back, we usually these electrical engineers, these electronics electrical engineers, we publish our research articles in this IEEE. You must be knowing that. That is a publishing house, a well-known publishing house for electrical electronics engineers. And there they have marked this word as I should I say in their policy. If you are writing paper, right, you can't use this word master slave. So you have to use some alternative in there. So be careful while writing an IEEE paper. So in a master slave JK flip flop, output of master is passed to the slave, right? And that implies the total propagation delay is the sum of both stages, right? That implies TPD of JK, this master slave, will be equal to T master plus T slave, right? And T master is 6 nanosecond and T slave is 4 nanoseconds. So it will be 10 nanoseconds. Option is the correct answer. Now I have this question. I want you guys to solve it first and then I will show the solution. It should take 2 to 3 minutes. So I'll read the question. Which of the state diagram represents the following circuit? So a circuit is given to you guys and you need to just find which state diagram correctly represents it. Uh, just do it. I'll show the solution afterwards. Waiting for others also. I'll just wait for a couple of minutes and then I'll show the solution. So let me show the solution. So you can do it easily, very easily. It's not a big deal. So let me just ask you a question. So the expression y of 2 is to 1 mux can be written as a bar x0 plus a x1. That applies when a is equal to 0, y is equal to x0. When a is equal to 1, y is equal to x1, right? So x0 is basically your q bar. So that means when a is equal to 0, it will change its state from d to, it will change its state from q to q bar, because for x1 it's q right here. Basically what I mean to say it, if q equal to 0, q equal to 1, if my a is equal to 0, my output will be q bar. That means if I am at q equal to 0 or I am at q equal to 1, but my a is equal to 0, it will go to next, it will go to complement. Basically if a is equal to 0, this thing will be sampled here, so that means next it will be q bar. So when a is equal to 0, it will change its states. But when a is equal to 1, check here, a is equal to 1, output is equal to x1, which is q itself, so it will remain as it is. Next state will be same as previous state. So this is which option? Can anyone tell me which option is this? Correct. This is option D. I hope you got it right. Actually, this was not directly question from your this week's content, but I had taken it from your basic course, that digital circuits course, that is being floated in fall session. So I thought I'll just give a flavor of it as well. I hope it's clear, right? There are no doubts. Let's proceed to question number 7. We have a JK flip-flop with J equal to 1, K equal to 1, and has a 20 kilohertz clock input, right? The Q output is A constantly low, B constantly high, C 20 kilohertz square wave, D 10 kilohertz square wave. So we need to find what will be the output. So before we proceed, so we have, let's draw this table for the JK flip-flop, clock J, K, and this is your Qn plus 1. So when clock is equal to 0, this will be don't care. So what will be my next state? Qn plus 1. Let's brush up some basics. So what will be Qn plus 1? Q0 or Qn plus 1 will be simply Qn, right? The previous state. Is that clear? And when clock is equal to 1, this is 0, 0. What will be output here? Hold, right? That means Qn, right? Hold means Qn. Is that clear? But I have this one question. We also call it something else. This Qn. If Qn plus 1 is equal to Qn, we have another name for it. Hold is right. There's nothing wrong with hold. But we have another name of it. We say it at memory. Called memory. That previous state is well maintained. Then I have 0, 1. So what is my output? Next state? Correct. And for 1, 0, 1. And for 1, 1, correct. How is toggle represented? Qn complement. So what I have here is I have a JK flip-flop. This is J, this is K, whose input is 1, right? And I have my output Q. And this is clock. So let's draw clock waveform first. And I am assuming here it's a positive edge triggered flip-flop. So this is waveform for clock. Now I have Q. Let's assume initially it was 0. Why I'm drawing these dashed lines only here? Anyone? Oh, correct. So here I see a positive edge triggering. What will happen to my Q? Output Q? Yes, complementary. That means it will toggle, right? And what about here at this point? Same. Here, correct. So it will toggle. So if it was T, this is 2T. So output has a time period of 2T. What will be the frequency? Frequency will be 1 by 2T, and that is simply your F by 2, and that is your 20 by 2, that is 10 kilohertz. You can also write if your output is if your input conditions. Oh, am I audible? Can actually this got disconnected? My microphone got disconnected. Am I audible right now? Okay, actually microphone got disconnected, so sorry about that. So let me just put it on full screen first. So it will toggle, and you simply can write your output clock frequency f input by 2 raised power n, where n is your number of flip-flops connected. So here f is on n is only 1, so it will be f by 2, so it will be 20 by 2, 10 kilohertz. Now I have a question for you guys. Solve this. So the output of circuit is shown below. What will be its output frequency? So you need to tell me what will be the frequency of this circuit, which has a input clock frequency of 1 kilohertz. Correct. Option A is correct. So a simple solution is this: f output will simply be equal to f input divided by 2 raised power n. F input divided by n is how much? And how much is n? 3. And f input is 1k, so 1 by 2 raised power 3 is 8, and this is equal to 0.125 kilohertz, and that is equal to your 125 hertz. Option is correct. You can also draw waveforms for this, and you can see how it works. By the way, what will be the time period of this? If it will be 8 times, right, of the time period of input. Whatever will be the time period of input clock, it will be 8 times of that. Now let's move forward to the next question, that is question number 9. So basically this question usually is in digital circuits when we teach. This is quite important, and you expect one to two questions there, but here the course is completely different, so uh, these type of questions won't be coming here. But from a bachelor's point of view, to the students who are doing bachelor's, this question is somewhat trivial, but also at the same time important. And there are lots of questions you can construct around these type of problems, and I have shown in my previous course while I was a TA different problem sets based on this. So here I just given an idea about it. So this is basically conversion of one flip-flop to other flip-flop, right? So here there are basically 5 points to remember when you want to convert a one flip-flop to another flip-flop. So problem here is convert a T flip-flop to D flip-flop. So how you approach a problem like this? First of all, you have to identify which is the required flip-flop, which is the available flip-flop. So here required flip-flop is D flip-flop and available flip-flop is which one? T flip-flop, right? Because we have to convert T into D. That means T is available with us and required is T. So point one is checked. Now we have to make characteristic table of required flip-flop. So characteristic table of required flip-flop means we have to draw the characteristic table of D flip-flop. So I have here is D and I have here is Qn, and here I will write Qn plus 1. So it is 0 0 0 1 1 0 1 1. So what will be this? Yes, D, that is 0, correct. So this will be 0, this will be 1, this will be 1. So point 2 is also marked. Now we have to make excitation table of available flip-flop, right? So we have to make excitation table of available flip-flop, that is with inputs Qn and Qn plus 1, we have to write what will be T. So we know it's an XOR operation. 0 0 is 0, 1 0 is 1, 1 0 is 1, and 1 1 is 0. Am I right? Is that correct? Now I have to write Boolean expression of available flip-flop. So available is T and I have to write Boolean expression in terms of D and Qn. So looking at this thing, this is simply T is equal to dqn bar plus D bar Qn, and this is nothing but your T is equal to D XOR Qn. Now I have to draw the circuit. So how will I do it? I have T flip-flop here, and this is my, what should I say, input, which is basically output. This is Q and this is D. So this thing, whole thing is D, and this is made out of T. So this is how you construct a D flip-flop out of T flip-flop. Basically, construction of D from T. So this is just a basic question, basic trivial method. There are some questions, interesting questions that I have shown in the last course. You can check in my playlist. I think it will be around in week 6 or week 7. There are some interesting questions you can look at, but these are only basic. This is a basic course. So what the course we are right now dealing with is an advanced version, which is basically CMOS digital design, that is towards the CMOS part of it. But I just wanted to give you this idea of this, what should I say, sequential circuits and all. Now I have this question. It states that a 4-bit Johnson counter is clocked at 100 megahertz. What is the total cycle duration before it repeats? So I have a question. A 4-bit Johnson counter is clocked at 100 megahertz. What is the total cycle duration before it repeats? I want you guys to solve it first, then I'll show the solution. So please write down your answers when you have solved it. Well, a 4 with a question mark is not an answer, right? So before we start, so what is the name of another name of Johnson counter? Another name of Johnson counter is, there is another name for this Johnson counter. No, not ring counter, twisted ring counter. And this twisted ring counter or Johnson counter, how many states are there? How many states it count? 2 into n, and n is your number of bits, and there in terms of architecture, n also represents number of flip-flops. So it is 2 into 4, so 8 states it will count. So after 8 state, my cycle repeats. So basically, after 8 cycles, I have a repetition. So we can say that thus at 100 megahertz, the total cycle duration before we have a repetition, before we have a repetition is 8 into 1 by 100 megahertz, that is 80 nanoseconds, right? So after 80 nanoseconds, my states will start repeating. Now I have a last question for today's live session. It says that a system uses a master slave D flip-flop for data storage. The master latch has a propagation delay of 3 nanoseconds and the slave latch has a propagation delay of 9 seconds. If the setup time of the flip-flop is 2 seconds, the clock period is 12 nanoseconds. Will the system work correctly? Can anyone tell me what will be the answer? Will the system work correctly if I have the following numbers with me? So even when I found this question, I found it's quite simple, but it's quite interesting, right? So I don't know what you guys should answer. Probably this won't be asked, but this is a quite trick question, I must say. So basically, you have this, right? So T should be greater or equal to TCQ plus TPD plus T setup, right? For a correct operation. This is a well-known condition. So T should be greater or equal to T clock to Q is how much is clock to Q? So, okay, you can write it like this also. T master plus T slave plus T setup. You can write it like this also. And T should be greater or equal to T master plus T slave is 7 plus 3 and T setup is 2. So T should be greater or equal to 12 nanoseconds. And T itself is equal to 12 nanoseconds. So if you go by this equation, it should work correctly, right? But there is something, it's like it's working at the brim, at the just at the edge. So even if there is some slight variations, there is no room for variations. You can say that there is no room for variation, variability part. So it may not be robust. So to be honest, I don't know what should you write for this type of questions, and it would definitely not be asked in your exams. But the idea is, right, there should be room for variation. You just can't work at your maximum ability, right? You just want, you have this boundary and you put your all those things in boundary, and you expect there are no variation part that will hinder my operation. So those things should be taken into account, and for that, you can say if you are talking about variation part and room for variation, it won't work properly, then it's no. But if you are saying everything else is ideal, then it will work, then it's yes. So in that way you can say yes or no. But this is wanted to give an idea, so don't go what should be an answer. I think if I wanted to answer it, so if I'm being taught about the non-idealities and other stuff, I'll say no. But if everything is ideal, like we have assumed so far, it will be yes, right? So you can say yes or no. Both will be correct for this. So, as I already announced in at the start of the session, today's live session was pretty short because the contents were like that, and the assignment problems that I had to refer were also pretty straightforward. I tried to include some basic problems and try to give some overview of the sequential circuit as well. So, if you have any doubt, please let me know. And if you want me to repeat any, if you want me to repeat any if you want me to repeat any problems in the week 8 problem session, you can tell me next time. So what I want you guys to do is next live session is on 9th March. So 9th March up to 9th March, whatever problems you have doubt with from the previous live sessions, live problem solving sessions, just mark them, and if the number goes very high, then we can only pick few of them. But if the number is pretty low, I will discuss in the last week's live session. We'll devote half our time where we'll discuss previous live problem solvings. We'll discuss previous problems, and that will be a kind of a half an hour 45-minute revision class, and half an hour 45-minute will be for week weight content. If there are any doubt pertaining to this week's live session, please let me know. I think otherwise we can close our live session. Some questions from SM. Yeah, good afternoon. So here, yeah, basically based on the information that is present in the question, it will be basically T master plus T slave only. So TCQ will not be involved here. So it will be only that much. So in fact, TPD of that will be also overlapping with TCQ, right? So you got my point, right? So what I mean to say. So we say this TPD is coming from the logical block, TCQ is coming from the sequential block. Here we are only talking about the sequential block, so that will overlap with the combination block itself. So correct. Yeah, yeah. So that is here contamination delay, TCD, right? Here, this thing. You are talking about this thing, right? So basically, so this is a contamination delay. That is minimum delay that you can say that is being encountered in the register or combination block. Basically, if you check your lecture notes or you go back to some lectures in combinational circuits, your delay is not same always. It will not always be worst case. Sometimes the delay will be minimum, and that how it depends on whether a delay is minimum. It will depend on the combination of inputs. Sometimes my input combination will lead to a particular delay that is minimum, and that's what is being referred here. So that particular minimum delay is being in a register is being referred to as CD register, contamination delay register, and that minimum delay in combination block is being referred to as contamination delay logical block. Got it? Yeah, obviously, yeah, definitely. Correct. This part, if I have to talk about this figure, it will be just a second. If I have to talk about this figure, it will be this part for register, sorry, register, and this part for logic. So, Anirudh has had some questions from assignments. So, Anirudh, you are talking about the assignments that were given in NPTEL this year, right? So, do one thing. When we meet next time, just mark those questions and let me know. Then, in the last session, we will discuss them, right? I think DC VSL we discussed. You should not face any problem with the questions I also showed you were pretty. I think the level of difficulty was also high for them. Anyways, we will discuss them. So just mark them and please let me know in the next live session. And on 16th, we'll discuss them. And also to the other participants as well, please mark the questions whether I have discussed them or they are in the assignments. We'll definitely discuss them in the last week's session, apart from week 8 problems, because I can't discuss assignment problems that is being given. So if there are no further doubts, no further queries, we can close the session. I'll just wait for 2-3 minutes. Maybe there might be some query or suggestion, and then we can close the live session. So next week will be comprehensive problems related to sequential circuits. So even if the assignment problems are not, what should I say, that difficult or that mostly they were this week's live problems. This week's problems were pretty straightforward. But next week I'll make sure we'll discuss some comprehensive problems like we have been discussing so far. Even if you might have seen that our problems that we discussed in combinational circuits, they were much comprehensive, right? Can you please display the 10th question slide? By the way, since we have some time, apart from this lecture, the other lectures that we had, live problem solving session, were they up to the mark? Are you guys grasping everything, or do you want me to, or basically, I just needed suggestions, feedback. Probably this is not probably this is the last time I'm being the TA. Hopefully, by the end of this semester, I'll be graduating. So, any suggestions, any feedback, please let me know. Maybe in future, if everything goes well, I might be faculty in somewhere. I don't know. If there are, by the way, if there are any suggestions or feedback, uh, uh, please don't hesitate. Always write an email. I'm always open to suggestions, feedback from you guys. Okay, that's nice to hear. So, thank you guys for joining. We'll meet next week. Thank you guys. Thank you. Thank you. Thank you so much.